In first year chemistry, we learned how to write chemical equations and balance those chemical equations, but we never really took a look at the fact that those reactions probably occur in a series of steps. So we need to talk about reaction mechanisms. A reaction mechanism is a series of elementary steps by which a chemical reaction occurs. Most reactions have almost an unlimited number of possible reaction mechanisms, so there's multiple ways that a reaction might occur. In order for a reaction mechanism to be valid for a particular reaction, however, it must meet two criteria. The sum of the individual steps must give the overall balanced equation for the reaction. And the second criteria is that the mechanism must agree with the experimentally determined rate law. In a reaction mechanism, there is a rate determining step. The rate determining step is the slowest step. It therefore determines the rate of the reaction. So the experimental rate law must agree with the rate determining step. The best way to illustrate this is through an example. So let's take the reaction illustrated here on the screen. The experimental rate law was determined, just as we showed you in the previous podcast. It was determined by looking at data and calculating the exponents. So the rate law is R equals K NO quantity squared H2 to the first power. So if we looked at the following reaction mechanism, and this is just one possible mechanism, there are two steps in this mechanism. If we look at the first step at the two reactants there's one H2 and there are two NOs. Now, in a mechanism, you can actually take the coefficients from the reactants and they become the exponents. Now, this is not done when you're determining the experimental rate law, but when you're trying to determine whether a mechanism is valid or trying to determine the rate determining step, you can actually take the coefficients. The coefficient in front of H2 again is 1. The coefficient in front of NO there is 2. So if you put those in a rate law, rate would equal KH2 to the first power because of the coefficient, and then NO squared because of the coefficient. So therefore, step 1 agrees with the experimental rate law. So that would be called the rate determining step, or more simply, it would be called the slow step. Now, sometimes in a reaction, you have substances that appear in the middle of the reaction in the steps, but they don't show up in the final balanced equation. So if we look at the same mechanism there and we look at the overall reaction, if you look specifically at N2O, N2O is boxed in there. N2O actually would cancel out when you add the two reactions together. So therefore, N2O is considered an intermediate. So it forms during the process of the reaction and then it gets used and it reacts, and so it does not show up in the final reaction. Okay, so remember that with the reaction mechanism, two criteria. The reaction mechanism must add up to the overall balanced equation, and the slow step, or the rate determining step, the rate law of that step must agree with the experimentally determined rate law. Now, we also should take a look at how reactions occur at the molecular level. Molecules, of course, must collide to react, but only a small fraction of those collisions actually result in a reaction. Now, what could be the reason for this? Well, collisions must have sufficient energy to produce the reaction, so they must equal or exceed the activation energy. Remember, the activation energy is the energy needed to get that reaction going. And just like in a puzzle, using puzzle pieces, the colliding particles must be correctly oriented to one another in order to produce a reaction. So they must kind of fit together like the pieces in a puzzle. Now, lastly, a few factors that affect the rate, and many of these you may already be familiar with. Of course, increasing the temperature always increases the rate of the reaction because you're getting more frequent collisions and you're also getting more energetic collisions. Increasing the surface area also increases the rate of a reaction. You have more spots there for a reaction to occur. Increasing the concentration usually increases the rate of the reaction. That would be if the rate of the reaction is dependent upon the concentration of that particular species. It would increase the rate. And then finally, a catalyst would increase the rate of a reaction by simply lowering that initial energy, lowering the activation energy by providing an alternate pathway.